So center of the mass principle is, suppose we have some kind of shape right there, right? And let's say this is a two-dimensional shape, and the book uses the term lamina, right? What the hell is a lamina? It's just like tiny little thingy, right? Flat. And then let's say we have this little, tiny little section. This is my dA, okay? So this dA, this side is dx, and this side is dy now, isn't it? Okay, now, and so far, only thing we have been dealing with is the constant density, A. But say our density is not so constant, okay? Then my dm, tiny little mass, that integrand that we are going to calculate, happens to be some kind of density function, sigma, which is a function of both x and y, depending on the coordinate. This may or may not be constant, but in this section, it's not going to be constant. And then times dA. You know what I'm saying? dA being this little tiny area. You get that concept? The volume density versus the area density and the length density. We are used to this, right? Okay. Then, in our case, this is sigma, function of x and y, two variable function, and then dy dx, right? Okay. I hear myself. Okay. Then, in case you wanted to do this in polar coordinate, that's sigma, and then we have to convert this into r theta. And then, not to forget, r dr d theta. You know what I'm saying? Okay, so what do we do? How do we calculate the mass? Because we need a mass in center of mass problem. So our mass will be, it's just a double integral of this region, whatever we call it, d, of sigma and then dA. You know what I'm saying? That integral. How does that calculate center of mass then, right? Okay, now center of mass, I'm gonna throw the coordinate here. So that same picture. And then I'm gonna copy that thing. And then put it here. Okay. Actually, I'm gonna move the whole thing to the left a little bit. Okay, and down. Okay, the idea of center of mass is that here is a, let's say center of mass is right there, right? Looks like it. But it doesn't need to be at the center because the density function, we don't know how that density function, right? Center of mass in x direction, we have to calculate this thingy. M times x bar will turn out to be double integral of this region D, and then our density function. And then we have to put another x here. Did that make sense to you? The coordinate position of x. This is a position of x. So that torque, you know that these are represents the three little kids on the seesaw. Each position times their weight is this thingy, isn't it? And then this is the center of mass, x bar right here. So the idea of center of mass principle is this entire body acts like a point mass at its own center of mass. You know what I'm saying? I think you're forgetting this entire center of mass. Okay, imagine this thingy is hanging on and then exerting a torque, right? So it wants to rotate, fall down, but then it hinges on this left-hand corner somewhere, right? So the torque exerted by each of these molecules in this lamina, all of them, which is mg idea, this mass, and g is on both sides, so that got cancelled, times that direction, that distance, right, added up together will be exactly same as if this is only one point mass right here times that distance. You know what I'm saying? Do you remember that discussion? Right. So this, and then of course your center of mass x here is whatever you calculate, this integral divided by your m. You know what I'm saying? So in reality, I mean, if you want formulas, it looks like this, but we never do it this way. X dA divided by your integral, oh, that's ugly. Just our mass. You know what I'm saying? This is the center of mass formula, if you will. But in reality, we'll calculate this mass separately, and then we'll calculate this, and then we just do this divided by this. You with me? And then center of mass for y and everything else works out exactly the same way. Okay, we'll take an example. Okay, so we have this thingy. Okay, and density of this lamina, only thing we know is proportional to the distance from the center of the circle. Okay, wow, how do we even, right? So our density function right here, which is x and y, and is proportional to some k. And what's the distance from the origin? Would that be square root of x squared plus y squared? Eh? Say yes. Okay. Okay, then shall we calculate the mass first? Yeah, let's do that. So your mass, change the color. Your mass will be the double integral of our thingy over this region D. Now, looking at this region, something tells you that you need to go polar, correct? Right, the shape of the region tells you that, of course, we should go polar. So what is this thing sigma in polar coordinate? R and theta. Oh, that's just KR, huh? Ain't that convenient? Yeah, more the reason to go polar. Okay, so we have K, R, and then we have another R, d theta. R will vary from 0 to A, according to our picture. That's ugly A. And then theta will vary from 0 to pi A. Who's lost? Y'all with me? Okay, let's evaluate this. So 0 to pi, and this thingy becomes 1/3 A. So we have KR cubed, therefore 1/3, evaluated from 0 to A, and that just becomes K over 3 A cubed. You with me? What am I doing? I forgot to evaluate with respect to theta. Okay, so that thingy now is evaluating, integrating with respect to theta. Do you see you just pick up pi? Or do you want me to integrate it for you? So this thing just becomes K pi over 3 A cubed. A? Are you with me? Okay, now, then we have to calculate this with respect to x and with respect to y, right? Guess where the center of mass in x direction should be? Do you see the symmetry tells you that it has to be right here? Or do you want to do it? I mean, we can do it, we got time. How many of you want to do it? Nah, nobody? Okay, just the y direction, right? Because like it has to be somewhere here. Shouldn't it be lower? There are more stuff here, but then it gets heavier as you go to the outer edge. You get it? Okay, so let's calculate this thingy. So I will say, change the color now, my, right? Kind of this thingy that we did here. Okay, that's a double integral of exactly the same thing, 0 to a and 0 to pi of this thingy, kr, right? I'm gonna write it a little more abstractly to over our d, and then this thingy, and then we need to stick y in here. You get it? Okay, I'm gonna move this thing over a little bit over here to get more room. That didn't work. Hold on. Why did that not work? Okay, good. Okay, now then we can have, how come my second integral sign turns out to be ugly? And 0 to a and 0 to pi, and then our density function was kr. Good. And then what is my y? What is y in polar coordinate?
R sine theta.
R sine theta, right? R sine theta. Good. So putting it all together now, we get 0 to pi, 0 to a, and then we have k r cubed. Good. And then sine theta, dr d theta. How about that? Okay, and then it's all downhill from here. So 0 to pi, and this will be r to the 4th, therefore k here and 1, write it as k over 4. And then 0 to a, and then we have sine theta, d theta, 8. Okay, substitute a, and this becomes k a to the 4th over 4, constant outside, and then this thingy becomes negative cosine a, and then from 0 to pi. You with me? And then do you see that you just pick up 2 from here? Right, too much integrity. So we have k a squared over 2. Good. Now you notice that I
a to the 4th.
Huh?
A to the 4th.
A to the 4th, of course. Nice catch. Okay. The reason I always call this my is then y is equal to this thingy divided by m. You get it? That's why I call it my. So therefore, my y, center of mass, is equal to this thingy divided by this thingy. You get it? Then it will have 3a over 2 pi. You get it? Easy enough? Okay, now I call it just my, center of mass, mx. Your book calls this thing, this entire integral, the moment. It's a stupid name. Moment. What the hell is moment, right? Well, but with this next name, actually it makes a little more sense, okay? because the next topic is moment of inertia. Remember that moment of inertia? Yeah. And your book calls this thing second moment as opposed to the first moment. You get it? Okay, so it's like, forget that. We're going to go with a physics term, moment of inertia. Okay? So suppose we have some shape. Not necessarily elliptic, but okay. And then suppose we have a tiny little thingy here. How come that didn't turn into square? Usually works well. Doesn't want to turn into square, so it's okay. Okay. Now let's zoom in and see what that thingy is. This distance right there is R, and this distance right there is X, right? Well, I'm gonna write it this way. That distance from the y-axis is what we call X. Distance from the x-axis is what we call Y now, isn't it? So if you remember from moment of inertia earlier chapter, that I, we call it, is the double integral over your region D. And then we had a density, right? And then we had R squared, right? You know what I'm saying? And that R squared, meaning if this is the axis of rotation is a z-axis, looking at it, and the whole thing rotates this way, right? Remember that mr squared thingy in moment of inertia? Do you remember forgetting it? However, now let's say if you want to rotate it, this is like, I'm going to call it Z, about the Z rotational axis. But we can actually rotate it about the x-axis, eh? If you rotate this about the x-axis, like this way, oh, that's y-axis, what am I saying? X-axis, this way, this is moment of inertia with respect to x. You know what I'm saying? What is our rotational radius here? Do you see that is y now? It rotates like this, eh? So then in that case, we have to put y squared here. You see why they are opposite variable? Well, x here and y there. Suppose we want to rotate this in about the y-axis. So this is the direction, right? This is what we call I of y. Then this x is the rotational, the radius now, isn't it? So in that case, we have to put xy here and then put x squared. How about that? And I'm going to put this thing down here as well. If you rotate it that way, that's what we call I of z, around the z-axis. And then everything else is exactly the same. Instead of just putting x, y, or r, we just put these things squared. And this, we don't have to divide by n. This whole thing itself is a physics concept, moment of inertia, that we did before.